Thank you for attending this meeting. So I'm just, as you know, this consists of a presentation of 20 minutes of the candidate, and you have the possibility of having giving questions to the candidate during 10 minutes or 15 minutes, we'll see. Okay. So just a short presentation of César Díaz Parga, who PhD is entitled Machine Learning Techniques for Prenatal Detection of Small and Vulnerable Newborns. The supervisors are Marta Núñez and Nicolás Vila. César is graduated in computer engineering at the University of Santiago de Compostela. He's a predoctoral fellowship from Junta. In fact, he changed the orientation, the subject, from object recognition in video to machine learning techniques to ultrasound imaging for detecting the fetal growth issues. And you did several different things. Among them, you was a participant in the AI Song Contest in 2023.
Yes.
Okay, there they recreated the voice of the mythic singer Anakiro. So he did a lot of different things, but today we focus on the thesis. Okay, thank you, César. So.
Okay. Thank you, Pablo, for the presentation. Today, I'm pleased to introduce my PhD research, as Pablo mentioned, entitled Machine Learning Techniques for Prenatal Detection of Small and Vulnerable Newborns. So, the main part is to talk about where this topic came from. This topic came from the Collage project. Collage is focused on developing reliable machine learning methods for early detection of small and vulnerable newborns, and which is the small size in a prenatal phase. So the main objective of this project is to improve the detection rate. And how can we achieve that? First, enhancing the understanding of etiologies or the certain etiologies of fetal growth. And in a second part, or a second way of achieving that, is identifying novel predictive biomarkers, which is the current line most related to my PhD. So, what is exactly born small? This condition has a name, which is small vulnerable newborn. This condition is determined by the satisfaction of one of these three factors. The first one is preterm, which is born before the 37 complete weeks of gestation. The second is to be small for gestational age, which has a birth rate below the 10 centile of the recommended international sex-specific standard. And the last one is to have a low birth weight, which is to have a birth weight under 2,500 grams. So once we have situated the problem or the condition, is this problem really significant? There are a few factors that allow us to realize the magnitude of the problem. The first one is that it occurs in 1 of 4 babies, which is a high rate. The next point is it's one of the greatest neonatal mortality reasons. And the third point is it has a great influence on developing chronic illnesses or chronic diseases. So now, if we take a look at this graph, we see how a vulnerable mother and fetus can end in miscarriage, maternal death, or stillbirth. And in the case of a live birth, this baby could die or even develop some kind of chronic illnesses that will affect in its life. So clinicians above address the problem with an approach which is early preterm diagnosis. So how can we do that, or how can we do this diagnosis? using this type of test. The first one is image test, laboratory test, or previous pregnancy studies. But these techniques are really different, but we now are focused on fetal ultrasound images because it's non-invasive, it's portable, and it's the most accessible one, mainly because of the equipment cost. So we are selecting this one to make this investigation. But what are these phases, or how can we do that? The first stage is to select the plane of classification. The second phase is measure the interesting areas, and the third phase is the gestational age estimation. So, taking into consideration the first step is estimate the optimal plane for the measurement. So, this one is the most complex task due to the fact that when taking the measures, two variables are introduced that make it difficult to obtain good quality data. So, we have in the first point the alterations of the movement of the transductor, which is the device used to take the images, which is, if we return to the previous slide, this device, and we have these 6 common movements, and these six common movements introduce some kind of noise or variations in the angles of the image taken. So the other problem is like the orientation of the fetus itself. Not all the pregnancies have the same fetus orientation or uterine orientation. So once we have estimated the correct plane for taking the measures, the radiologist select the interest areas. So the first one we have here is the head circumference. This is the biparietal diameter, which is a diameter of the small diameter of the ellipsis. Second one is the abdominal circumference, which delimits the abdominal area. And the last one is the femur length. So, as we have that, these measurements are combined using this kind of equation or other different equation to predict the gestational age. But the main question that you make is, why this is actually the gestational age? So the gestational age, as you can see here, is the age of the fetus calculated from the first day of the mother's last menstrual period. But this date is not as accurate as you can think. So there is some kind of uncertainty, in determining the LMP. So we need an alternative approach to address this problem. In this case, the alternative is using ultrasound measures or using estimations over ultrasound measures. So how can we do that? This is used a combination of indicators, as you can see in the previous slide, just these indicators, to obtain an equation that can predict the gestational age, which is the same as you can see in the previous slide. So the question of most you can make now is why we need that. So the reason is that it helps estimate the fetus expected age. So it allows us to determine if the fetus are following normal behavior in their growth, or there is no alterations in their growth. So it could be that estimated gestational age, looking at these equations, could not be general as we can think, because these kind of equations with these fixed numbers are not possible to encompass all the regional and ethnic diversity. So the clear answer of this question is, are these equations general? No, because these equations are created for specific populations. For example, this graph is from a Canadian population, and other kind of graphs similar to this are from American, German, and British associations. So in addition to these factors, enter to the variability of the growth, genetics, maternal health, and environmental factors. So this leads us to a conclusion about this part, which is the no single equation is able to cover everything. So we find that these equations widely used in the world to predict this gestational age are clearly biased. So the presence of bias is inherent to equation created for one population and applied to other different populations. So once we have this contextualized, you can understand that the problem is very broad and complex. So now I'm going to explain particularly what is the focus of this work, of my PhD current line of investigation. So we have three main objectives, which is find a method to classify ultrasound planes, the first one, addressing the problem of intrauterine and proof-induced motion, creating an automated mechanism to segment the regions of interest for growth measurements, and the last one is to develop a growth model that accounts Díaz data for accurately identifies the condition of the small vulnerable newborn, considering or taking into consideration the specific context that made this, for example, this variability appears. So how can we do that? First of all, we need to introduce our data. We have three types of data. The first one is for plane classification, for fetal anatomy segmentation, and for gestational age. For the first case, we have two databases. The first one, which is around 12,400 images, and a phantom database, which is the second one, which is a database recollected from models used to train radiologists on their operations. It's not a real database, it's taking over models. For the second case, we have four databases. The first two of this one, the first two, contain only brain segmented images, and the third one only is annotated by us. So we introduce the abdomen and femur to provide more variety to the data that we can obtain at the first moment. And the last one, which could use at the third stage of the predict the gestational age, is a database came from the BC and Natal Center, and will be relevant for this phase. But now the size and the data are in current study, so we have to determine the number of the instances that this database has. So we now move to the current challenge of this investigation. So there are a few key challenges shared by plane classification and segmentation tasks. So they are mainly limited by the amount of label data and the image variability, due to things, for example, as I mentioned before, that is difference between the ultrasound machines. The ultrasound machines are not the same. In most of the cases, it's impossible, and the movement of the fetus itself in the uterine in the uterus. So the first task is plane classification. So the first point is that there is a lot of ambiguity in plane annotation, specifically when we are selecting the optimal plane in each case. If you take a look at these two images, which are a bit shadow in this projector, but the first one is more with a high resolution in the terms of you can see no borders or no big shadows in the image. But the second one is more clearly or have more contrast, but is not as quality as the first one. So both are femur planes, and both are femur planes used to measure this area, or to measure, or to select to measure the femur. So this is a kind of difficult task, and this introduces ground truth ambiguity. And also, we have real-time constraints used to, for example, measure a fetus over a proof induction real-time assessment task, which is more important in the clinical practice in certain moments. So if we move now to the segmentation part, we also take anatomical and segmentation structures, and we have four more problems to solve that. The first one is the complex anatomical structure. So we have talking about overlapping or unclear boundaries, specifically in structures like, for example, brain ventricles. So if you see this green and blue area, we have small and different structures to predict this anatomical structure. So it's difficult to segment it over a big region that is the brain. So other question to take in account is the low quality with noise, shadows, and artifacts, as you can see in this image, for the segmentation tasks, which are in the mostly the same planes as you can see here for labeled data. So other key problem is this word, as you can see here, is gold standard. Gold standard is the best available reference, usually based on expert input. We don't have a real ground truth. So these data are labeled from experts. It's not the real data that you can contrast your results. So this data, even being a gold standard, it has some kind of variations due to the interoperability observers, because some radiologists could label just here with a well-defined counter, and for the femur task, we have a rectangle like this. So this is a kind of ambiguity that you can see in most databases. And the last one is the variability due to maternal factors. As I mentioned before, the position in the uterine is really difficult to find or to locate a specific position for all over the fetus and all over the pregnancies. So it's difficult to address this kind of problems. So once we have the challenge situated, we have to evaluate how our model performs. So we are going to use two types of metrics. For the first stage, we are going to use typical metrics using in classification tasks as accuracy or F1 measure. And for the second task, for the segmentation metrics, we are going to use Díaz score and 95 percentile of house door distance. So the first one represents the area overlapped between the prediction and the gold standard. And the second one represents the distance which measures how closely the predicted and the golden standard boundaries align. Focuses on the largest discrepancies of the 90 percentile points. But it ignores the 5% of extreme values, providing a more robust way of measuring it. So to our problem, we want to maximize this score and minimize this other. So we have to be more overlapping between prediction and the gold standard, and has minimal difference between the predicted and the gold standard area. So now we are going to move to the first of the problems, which is plane classification task. In this case, it's difficult to have large databases or a variety of large databases that allow us to capture all the existing variability. So we have two approaches. The first one corresponds to the most easy case, which is prenatal classification in large real data sets. The first one is trained over the first database that I mentioned before and evaluated over the same database. The second case is using a pre-training over the phantom datasets. We use this pre-training and we made a fine-tune using the same database and evaluate over the final database, which is the real database in both cases. So if we take a look at the results, we see the results in terms of accuracy and F1 score. We stand out the most that for a simple case or a less deeper network, is the case of ResNet, transfer learning performs well than the training in large dataset or the first approach. And for the second case, which is the opposite case, is you can see in the ResNext, which performs better or in large datasets than using the transfer learning approach. So this problem, as you can see here, is not solved because we have both different approaches, and we need to still investigating over this project, over this aspect of plane classification, and it's an ongoing work right now. So if we move to the segmentation task, I will make a bit introduction of this problem, which is using a kind of images obtained a segmentation bound, which is slightly different, as you can see in the previous image of radiologist annotation. So in this case, we want to obtain the abdominal circumference as well. And for that, we will base our research around the UNet architecture, which is widely used in medical image segmentation and provide the best results of the field. This architecture is based on contraction and expansion. We reduce the dimensionality of this image and we expand it to obtain the interest area segmented. So, however, instead of our investigation is based on the UNet architecture, we are going to we proposed some modifications taking into account this structure as encoder-decoder, interpreting it as encoder-decoder. So if we take a look at the first approach is the baseline or the more basic approach, which is using a UNet for the first case and for each case. And in these situations, we have one for brain, one for abdomen, and one for femur. And this lead us to obtain really good results in brain and abdomen, which are with a high Díaz score and a low Hausdorff distance measured in pixels. But the femur, as you can see here, it's complex task, so the results are expected that to be lower than the previous ones. So, once we have this, the first modification is reducing the complexity of the mechanism that we have used before. So, use a global encoder for the three tasks: the brain, abdomen, and femur, mainly motivated by the similarity or the same kind of problem for this task and the same type of image. So, the results, as you can see here, are really similar to the previous one, and in these cases, the results lead us to establish that we could do almost the same with only one encoder, reducing all of the complexity of the network. So, the problem appears when you see in the Hausdorff distance that a big difference or a big increase in the abdominal and femur area. So, motivated by this, we decided to propose other architecture, which is using a dual encoder, we use it for brain and abdomen structures, and a separated approach for femur context, which in the case of femur is the same as the baseline approach, and in the second one we can see that the Hausdorff distance is reduced from the previous global case. But these differences are quite similar, and we need to perform some kind of fair comparison between the data. So we use a statistical comparison based on the Kolmogorov-Smirnov test. So in the first, so in orange, we could see the best result for each particular case. So there are, in most of the cases, no substantial difference. As you can see, in femur there are no substantial difference, marked by an asterisk, just here, here, and here. For the femur case, there are no difference. For the abdominal case, there are only difference between the Hausdorff distance of the baseline and the Hausdorff distance of the triple. And in the bearing case is the most complicated task, or the most difference data between the baseline and the other approaches. So, in view of that results, there is also an open problem, and we are now still investigating in this and preparing other kind of solutions to address this problem. So, to make a final recap of our investigation and our project, the first point is that fetal plane classification is almost complete, but we are still in developing some kind of studies about the impact of the transfer learning. The second one is the segmentation of the growth measurement regions, or the growth regions, interest us for these measures. And we are, as I mentioned before, we are still developing a study. And the last one that you can see here, and that I didn't mention in my presentation, is future work, because we will start this phase when we obtain a new robust model capable of distinguish the best plane measurement and to segment accurately, and we are capable also to segment all the regions, all the interest regions over a particular plane. So that's all. Thank you for your attention, and we can open a round of questions if you want.
Okay, thank you, César. And you were in time, in fact. Yes, very 20 minutes. So we have questions. You want to ask questions to César, please.
Also difficult to obtain real specimen images.
What, can you repeat the question? I didn't listen, sorry.
Okay. Why is it so difficult to obtain real specimented images?
It's difficult mainly because you need an agreement between the patients, an agreement you have to anonymize the data, and we have to make a kind of groups or restrictions that you, for example, if you take a look at these images, it's difficult to obtain a big amount of data from each patient for each period and for each plane. So, for example, for one patient, you could also use one plane of this, or you could have one or two planes, because of the radiologist, it's not common to take a video of this assessment or diagnosis assessment because they only need one plane. So they only store the plane that they use. So it's difficult to create these databases, mainly due to legal restrictions and mainly because it's not familiar for radiologists to create databases, so they are only focused on the planes that they want. So the databases are really small because there are a few patients and few planes because they are not need all the planes and all the situations. They are only store all of they want, which are the best ones. So if you focus on distinguish between an optimal and suboptimal plane, you have difficulties of, for example, taking a good score. For example, if you take a score or a good score, the best to obtain the best score of a plane, the results could lead us to say we don't have this score particularly because this score of the optimal score this optimal score is not able to calculate it, sorry, because we don't have variety of planes. So there are optimal planes, no non-optimal planes, but on the second case we don't have one. So it's like an anomaly detection problem or similar to anomaly detection problem because there are all good planes but there are no abnormal planes. So it's difficult to. Sorry, I don't if I explain it really well.
Maybe I can say something. The main reason is because it is done manually, and clinicians are very busy all the time, and also they not very often like to share the data. So you need the agreement, you need to know them well, and they need to be, to work very often. They need to put many hours on this, and it's normal, but it takes a lot of time. That's the main reason I would say.
Thank you.
Congratulations on your talk. First of all, it was very interesting. I'm wondering why the weight of the fetus is not used as the variable for your model training.
The weight of the fetus, because if you want to estimate the weight of the fetus, you need to perform a similar equation to this one. There are some kind of equations for gestational age, and there are other kind of equations to predict the birth weight. So we are focus on the gestational age because to estimate the birth weight is a bit complex and in some cases is less reliable than the gestational age equations. So birth weight is a more complex task. So we are focused now in gestational age because it's a bit simpler than the other problem.
Right. It's just because if you are measuring the growth of the fetus, I think the weight is also an important, measurement in that, because you couldn't really know if, the length and diameter and everything else is proportional to the weight. And the second question actually is about it. If even you obtain all these measurements and you predict really if the growth is not going well, so the ethical, kind of applicability of your model, which would be it? Because, if even the experts will detect that on the early phase, because as far as I can see, you analyze the first trimester images. Then what would be the of the experts?
Okay. First, to address the first question. Okay, I think if we are moving to this picture, we could understand better. Because we are now focused on the gestational age because it's a sufficient condition to establish this vulnerable newborn. So to complement the models in a future, we could explore, so as you can say, the study of the birth weight, the prediction of the birth weight, and we could add, technical problems. So we could add these other variables to predict the SVM. So this is more than the later phase or the future work we are going to perform. So could you remind me the second question, please?
Yeah, okay, you detect it, so what would be the next step? Yeah, what would be the labor of medical workers in this case?
Yeah, the medical work after we detect the small vulnerable newborn is to provide some kind of treatment to the patient to correct this condition, because if we can determine it in an early stage of the pregnancy, it could be corrected. So, like, for example, vitamins or nutrition policies or some kind of these treatments, we could influence on these conditions, so it could be corrected. So the main focus of the project and one of my objectives is to create a model that could identify this in a correct way, because this is a problem that could be solved. It's not an impossible problem to solve. It's not complex to solve, but it's complex to detect. So the main task is detected, and with a good detection, we could also solve this problem and prevent of this phenomenon, which is kind of cyclical.
Right. Thank you very much.
Thank you.
More questions? One question? We have time for one question, if you wish. Thank you very much. But just one question. It's about just the related work, because I didn't see in your presentation what is the related work that the other strategies that want to do more or less the same thing to achieve the same objectives with other strategies. Can you compare your work with other related ones?
So at this moment, the only related work that we have for the first case is that, I will center first in plane classification. The related tasks, the related work are more commonly performed over the same databases and using, for example, a variety of neural networks that evaluate the performance on wider plane studies. In our case, we see that we only use at this moment 3 planes, but for plane classification in this database, there are a group of methods performed over 6 planes. So this is a particularization of a big problem of the plane classification, because we are only need some type of planes, not all the planes that are present in this database. So we take this related work and adapt to our problem. And for the segmentation case, for the other databases, there are a lot of works in unit architectures about unit or variations of unit, like NN UNet, which are mostly used in these kind of tasks. For example, in brain classification, there are a lot of works in brain segmentation, sorry, not brain classification. There are a lot of works using this architecture, variations of this architecture, because it's easy to prove, easy to understand the working of this network, and also it performs really well. So the related work in this sense says that this architecture is really good, and we offers the best results in the field. So these results could be comparable to the similar ones, only in this case, because abdominal and femoral are annotated by us, so we haven't got a real ground truth of it. So.
Okay, thank you very much. So we can read.